Okay, so it's time, Michael. I'll start, I guess.
Absolutely. You take it away,
Yeah.
Tajinda.
Okay, great. So, good evening, friends. We are very happy to have you with us here today for the seventh OSMU lecture of the year, which will be given by Bernd Henschenmacher. Bernd is currently working with the German Federal Office for Radiation Protection in the field of optical radiation. Earlier, he worked in bioelectromagnetics, and before that, for the German Aerospace Center in the field of space radiation biology. Bernd is a biotechnologist by training, and in his own words, he has this strange hobby of reading old physics papers and books and writing books about that. But I think he puts it lightly. He's a deep scholar, in my opinion. I have learned a lot about literature, especially on Jordan's work from correspondence with him.
Yeah.
And I'm happy to say that Bernd is, I think, the most regular and active participant of our OSMU lectures. And it's really a pleasure to listen to him on Jordan's attempts to generalize quantum theory, something that's very relevant for this series. Over to you, Bernd. Very happy to have you with us.
Thank you very much for the nice introduction. So now I can start with the legal disclaimer. What I'm going to say here has absolutely nothing to do with my job at the German Federal Office for Radiation Protection. I'm doing this in my spare time, and so this was the legal disclaimer. So this has nothing to do with the German Federal Office for Radiation Protection, and also has nothing to do with my work here. But now, okay, can you see my slides?
Yes.
You don't see. Okay, so then I will start. So unfortunately, this talk has to be postponed because I was ill in March. But now I can start, and I will talk about Jordan algebras and beyond on Pascual Jordan's attempts to generalize quantum theory. Okay, that's oh. Now have a problem. I cannot. I can. Okay, so I will start 100 years ago when Jordan was publishing his first paper ever, because this is important to understand how the formalism of quantum theory we use today was formulated and came into action. So the first paper Jordan wrote was on the way how to describe electromagnetic radiation, and he compared the approach by Einstein, who used the photon theory, so a quantized electromagnetic field, with the theory of Bohr, Kramers, and Slater, who tried to uphold the continuum view of electromagnetic fields. The difference between Einstein and the BKS theory was, I have a little trouble seeing my own slides at the moment. Maybe I can. Okay, problem solved. The important thing, the difference between Einstein's proposal and what later became quantum theory and Bohr, Kramers, and Slater theories was that in the BKS theory, energy and momentum are not conserved in individual processes, only individual, on the average, average, do we have an energy and momentum conservation, but we don't have a strict energy and momentum conservation. So, for example, the interaction between a photon and an atom once does not need to conserve energy and momentum. This was the crucial difference between Einstein's photon theory and the BKS theory. And okay, I was too optimistic. I do have, okay, sorry, I have a delay. If I push my button, it takes the time before. Sorry for this. So this was what I just said. So only the average energy and momentum values of in this case, the electromagnetic field were conserved in this theory. And this theory was objected or criticized already from the start, because people noticed even if you have an average conservation of energy momentum, then you will have fluctuations, and these fluctuations of the conservation or also of the average momentum and energy conservation will start to grow, and then you in the end you also end up with not only with an statistical violation of energy and momentum conservation, but also in the long run with a general violation of energy and momentum conservation. This was the reason, apart from the fact that the experiments by Geiger and Compton showed that there is a conservation of energy and momentum also in individual processes. Apart from this experimental finding, also the trouble that you cannot explain where we don't observe larger fluctuations in energy and momentum conservation was the reason why the BKS theory was falsified or was given up. And originally in his paper from 1924, Jordan compared both theories, so Einstein's proposal and the BKS theory. And at that time, he was not sure, or the scientific community in general was not sure which theory was right. But the fact that the BKS theory proved wrong was crucial for Jordan's development of a scientific career in the following about 30 years, because after this, he always tried to make sure that any theory he was developing obeys energy and momentum conservation. This only changed in the 1950s when he was working in cosmology, developing his own scalar tensor theory of gravity. More about this later. So why is this important? This is important because, sorry, I have to go back. Because later on, Jordan compared different theories with different statistical properties. And von Neumann concluded from the failure of the BKS theory that you have to be careful in introducing stochasticity into physics. Because in the BKS theory, the energy momentum non-conservation was linked to the fact that before a measurement, you don't know the exact values of energy and momentum. And also afterwards, there's a certain probability for a system to jump into a different state with different energy and momentum. So in quantum theory, we do have the fact that we don't know in advance the results, so we can only give probabilities for measurement results. But in the traditional formalism, a measurement moves the system into an eigenstate. And if the system is in an eigenstate, then we can with certainty give propose or predict the values of a measure of results. So after a measurement, we know with certainty the values the system has when it's in its eigenstate. And this is something which distinguishes quantum theory from the BKS theory, and also from many of the theories I will introduce or describe later on. So then we go to the in the year 1925. This was the first paper together with Max Born on quantum mechanics, very famous paper, where they introduced the formalism of matrix mechanics. The fascinating thing about this paper, apart from introducing quantum mechanics, it was a crucial milestone in the history of science, is a footnote which appears in the last part of the paper. And this footnote was added by Jordan in the last part of the paper. Born and Jordan proposed also to quantize the electromagnetic field. So not only quantum mechanics, so quantizing mechanical system, but also quantizing field theory. This was the first step in the very first step, admittedly, in the direction of quantum field theory. And in this paper, Jordan and Born replaced field strength by matrices. So they quantized the field strength of the electromagnetic field, but they did not quantize space and time. So the matrices which describe the field components of the electromagnetic field still contained numbers describing the space-time manifold, but this was numbers. It was not related to matrices. So the coordinates of the electromagnetic field were still treated classically as real numbers, as usual coordinates. And Jordan added a footnote in the section where he said, maybe we need to also introduce matrices to describe space and time for the electromagnetic field. And this is one of the probably the earliest hint that we have to go to non-commutative geometry or to a quantum geometry for describing physics and the electromagnetic field. This was not followed up, at least not initially, because in the follow-up paper with Heisenberg, Jordan, and Born noticed that the formalism they had, so quantization of the electromagnetic field without quantization of space and time, was sufficient to describe observations at the time, and so they did not follow on this in the 1920s. What is also interesting concerning generalizations of quantum mechanics is a paper Jordan wrote, two papers Jordan wrote in 1926 and 1927 on a new justification of quantum mechanics, so a new way to introduce quantum mechanics. In this, he was willing to use non-Hermitian and non-normal operators, which is quite radical, or how do you say, distinguished from the way quantum mechanics was later introduced and is used until today in most cases. The reason for Jordan to do this was basically not because he wanted to generalize quantum mechanics. The quantum mechanical formalism was still to be developed at that time. It was basically a hangover from classical mechanics, where you have canonical transformations between momentum and precision operators, and Jordan directly tried to transfer this into the new setting of matrix and linear operators. And he was still close to the correspondence principle, and that was the reason why he also used certain canonical transformations which transform Hermitian operators into non-Hermitian operators. The only thing which is preserved in this case is the spectrum. Jordan then also noted some important and interesting facts about the rule Hermitian operators have, or later self-adjoint operators, because he looked at continuity equations or conservation laws, and he noticed that for example, the Schrödinger equation to be to preserve probability densities, the operators appearing in this equation need to be normal, so they need to commute with their adjoints. And this was one of the reasons why he did not follow on this proposal to also use non-Hermitian operators for quantum theory, because then you got into trouble with the continuity laws. Okay. What's interesting from our perspective today is that in this paper, Jordan still used a time operator to describe time, so the time used to measure a system or the time it takes for a system to evolve. And he also uses a non-Hermitian time operator in this paper. One thing which is quite interesting, and there's a very interesting paper I would really recommend you to read. It's long, but it's really fascinating because it discusses these two papers at the early days of quantum theory. We have another problem if you use non-Hermitian operators. How do we get real and positive probabilities? And Jordan tried to use what he called supplementary amplitudes. These are basically complex conjugated amplitudes which combined with the original amplitude give a real number. And Duncan and Jensen showed in 2013 that Jordan's procedure would work for normal complex operators, for example, for unitary operators, but it does not work for non-normal operators. In this case, you don't get the right kind of probability distribution. And this was also the reason why Jordan stopped his work on non-Hermitian operators quite early on, because he could not find an appropriate probability distribution, a way to calculate probabilities with this setting. But important for us is that even in the early days of quantum theory, people were playing with the idea to use non-Hermitian operators and not stick only to Hermitian operators and unitary operators to describe the time evolution of quantum mechanical systems. And it also shows that Jordan early on was open to new ideas and to a less restrictive way of dealing with the formalism of quantum theory. So this didn't start with Jordan algebras. This is what I wanted to convey with this. So Then, at the same time, in parallel to Jordan, John von Neumann was developing the formalism of quantum theory, and basically he laid out what we use today. So observables are described by self-adjoint operators on a Hilbert space. In the finite dimensional case, we have Hermitian matrices, and canonical transformations and time evolution is given by unitary operators. And the unitary operators can be formed from the Hermitian operators by multiplying the Hermitian operator with the imaginary unit, and then form the exponential of this. So then we have here a tight link between Hermitian operators and the generators of symmetries and time evolution, the unitary operators. And in his second paper, Jordan adopted this approach by von Neumann, and von Neumann's work on the foundations of quantum mechanics had a really strong impact on Jordan, because after 1927, he never tried to use what's later called non-formally real algebras, so algebras which are complex or don't give immediately real values, but more about this later. So we have an early attempt by Jordan to go beyond the formalism of quantum theory, but then John von Neumann showed that unitary evolution and Hermitian operators give the right kind of probability rules, and of course they ensure that we have conservation laws. Okay. Then in 1930, Jordan and Born published one of the first textbooks on quantum mechanics. And in this textbook, they still were proposing that one should use a non-commutative time variable that does not commute with the Hamiltonian of the system and does not commute with the position and momenta of a particle. So in 1930, they were still trying to introduce a time operator into quantum theory. At that time, they said that they will describe more about this in the second edition and the second volume of this book, which has never been published. They just mentioned that they cannot introduce a time operator with matrices with discrete eigenvalues. And this was never done, so they promised to introduce this later. The only thing which is fascinating about this book from 1930 is that Born and Jordan used a pure matrix mechanics formulation. They tried to avoid the use of wave functions and wave mechanics. At that time, it was known that there's an isomorphism between matrix mechanics and wave mechanics. Jordan and Born were aware of this, so they did not ignore the findings and the success of wave mechanics. It was more that they felt that wave mechanics have some trouble later on it with, for example, with the relativistic formulation and also with the measurement problem, and they wanted to present a formulation of quantum mechanics which does not rely on wave mechanics. And Jordan's hope was that this matrix mechanics formulation, by being more algebraic, would also be more suitable for necessary generalizations of the formalism of quantum theory. That was the reason why they used matrix mechanics. And it's true that the matrix mechanics school in Göttingen and the wave mechanics school in Vienna had some dissent for some time. I think it's fair to say that there was some struggle between both groups before wave mechanics took over. Okay. Another thing which happened in the year 1930 was a paper who Jordan wrote together with Vladimir Fock, the guy who later introduced the Fock spaces, on uncertainty relations for the electromagnetic field. They used the electron, a point-like electron, as a probe to measure the electromagnetic field and the field strength, and they tried to develop uncertainty relations using this approach. And what's interesting is that they found that they got triple uncertainty relations, so not uncertainty relations between two pairs of observables, but uncertainty relations between three different observables. And this later proved crucial for Jordan's work on non-associative algebras and attempts to go beyond quantum theory using non-associative algebras. Okay, go on. I make a short break here. So this was the introduction to the formalism of quantum theory. And oh, there's already something in the chat. Are there any questions or comments? There was a question from YouTube. The book is called so it's in German, zur Quantenmechanik. So it was published in 1930 by Springer. It has not been translated into English in the last 94 years. So it's just called Quantenmechanik or quantum mechanics in German, and it has never been translated into English. I'm sorry for that, but yeah.
So it's very nice. Sorry to interrupt you. Didn't hear Heisenberg's name in all this much so far. So, but it's called Heisenberg's matrix mechanics. So can you please shed some light on this fascinating aspect?
Of course. So I was just a little bit jumping over Heisenberg. I'm sorry for that, but of course. So the first paper Jordan and Born wrote together was only Jordan and Born. But apparently also Heisenberg was working at the same time on the quantization on quantum mechanics, and then he had his epiphany when he was traveling to Helgoland because of some health issues with allergies, and then he noticed that the spectra of Fourier coefficients, which were used in the quantization procedures of the time, could be linked to matrices, and then he wrote back to Born, and then something wonderful happened. Born was talking to his students during traveling in a train, and Jordan listened to Born, and Born was talking. Yeah, Heisenberg found out that there's something with matrices. I don't know much about matrices, and then Jordan stepped in and said, I know a lot about matrices, because Jordan at the time was an assistant to Richard Cohen, a German mathematician, a very famous German mathematician with a French name. And he knew a lot about matrix mechanics. And so Jordan and Born teamed up and wrote the first paper on matrix mechanics together. And then they wrote, of course, when Heisenberg came back, they all three worked together on the second paper on quantum mechanics, which then also appeared in 1926. And this really laid out the formalism of matrix mechanics, so that you have to that you can describe observable quantities like position and momentum by infinite dimensional matrices at that time already, and that you need similarity transformations in the general sense to describe how to get the spectrum out of the matrices and to describe dynamics. And then they also noticed that they have to use orthogonal matrices, which was later named unitary matrices in the paper. What's also fascinating is that at that time, they really tried to use a discrete formalism. So instead of a normal integral to define the Lagrange function, they used a trace over matrices to define an integral, to define a Lagrange function or matrix function in this case. And they also continued their work on the quantization of the electromagnetic field. Interestingly, later on, coming back to Jordan's ideas from 1926, later on, when Heisenberg was developing his unified spinor theory in the late 1940s until the late 1950s, he used non-Hermitian matrices. For some time, he tried to use non-Hermitian matrices because one of his students found out that if you use non-Hermitian matrices, you might be able to get around the infinity problem quantum field theory had to face. Unfortunately, there was a good working collaboration between Jordan, Born, and Heisenberg on matrix mechanics and Hermitian matrices and unitary matrices, but this was unfortunately not continued. So there was still an exchange of letters, and they took ideas from each other. Of course, for Born, it became later very much impossible to continue working together with Jordan and Heisenberg because Jordan became a Nazi and Born was a Jew who had to flee to the United Kingdom. But unfortunately, I would say this was a huge tragedy. As we always see later, there was no longer a strong collaboration between the three men after developing the formalism of quantum mechanics, also when they worked on quantum field theory. So they were papered together where, okay.
Thank you very much.
Yeah. So I don't want to skip over Heisenberg, but I have already so many slides that I had to make a compromise. But one can give also a talk about Heisenberg's unified spinor theory. This would also deserve its own talk because it's also fascinating. But now we're going back to the Jordan algebra. So we stopped when Jordan and Fock found out that there might be triple uncertainty relations for the electromagnetic field in an attempt to unite relativity, field theory, and quantum mechanics. And Jordan was in the 1930s working together with, today we would say Russian and Ukrainian researchers. At that time, it was just Soviet researchers in Kharkiv, so in Ukraine. And his work on Jordan algebras actually started in Kharkiv together with Igor Tamm and Fock. So he drew some inspiration and worked together with these two Soviet researchers. But this collaboration somehow ended, and there was never a joint paper between the three persons. He just took this as inspiration and later worked with two other famous researchers, as we will see later, on Jordan algebras. So why did Jordan look for Jordan algebras? There were two reasons. First, he felt that the formalism of matrix mechanics he had just developed 7 years earlier was not suitable for the unification of special relativity and quantum mechanics. There were a lot of problematic aspects of quantum field theory in the 1930s, and Jordan thought this is basically due to the fact that the formalism of linear operators on a Hilbert space is not suitable enough to unite special relativity and quantum theory. And the other thing was Jordan noticed that the observables of quantum theory do not form an algebra using the ordinary matrix or operator product, because if two Hermitian matrices or two self-adjoint operators do not commute, the product, the ordinary product of two self-adjoint operators or of two Hermitian matrices is no longer a self-adjoint operator or a Hermitian matrix. So the observables of quantum theory are not closed under ordinary multiplication. And Jordan tried to fix this and find a formalism where you can only use mathematical operations which have a clear physical meaning. So the ordinary matrix product does not have a clear physical meaning, because the product of two Hermitian matrices, if they not commute, is not a Hermitian matrix, and so not an observable in the sense of quantum theory. So it does not have a direct physical meaning. So he looked for operations which do have a clear physical meaning. This is the addition of Hermitian matrices. So the sum of two Hermitian matrices is a Hermitian matrix. The squaring operation, so multiplying a Hermitian matrix with itself, again gives the Hermitian matrix itself. You can also form functions of Hermitian matrices if you use one Hermitian matrix. So you can form function in one variable. For two Hermitian matrices, it becomes more complicated because they don't commute. But the squaring operation of one Hermitian matrix and the addition operation of Hermitian matrices do have a clear physical meaning. And Jordan tried to use the squaring operation and the addition operation to define a new multiplication, which also should have an immediate and clear physical meaning. And this then later led to his Jordan product. So this is the formulation you always find. So it's 1/2 of the anti-commutator. And the nice thing about the Jordan product is that Jordan product of two Hermitian matrices is always a Hermitian matrix. In the infinite dimensional case, things are getting more problematic, because you have to take care of domains and definition. And even in the infinite dimensional case, it can be the case that even the Jordan product of two self-adjoint operators is no longer a self-adjoint operator. But in the finite dimensional case, this is always the case. And there's also an infinite dimensional generalization of Jordan algebras called Jordan-Banach algebras, and they are really can be used as a tool to model at least the observables of quantum theory. What Jordan also found is that his new product is commutative but not associative in general. So if two Hermitian matrices do not commute, the Jordan product, and under the ordinary matrix product, the Jordan product is non-associative. So in a sense, you exchange associativity and non-commutativity with commutativity and non-associativity if you pass from the matrix product to the Jordan product. And this makes sure that for the Jordan algebras Jordan first found, the first Jordan algebras Jordan found were basically Hermitian matrix algebras, which the Jordan product. And because in this case, the Jordan product is coming from an associative product, it cannot be arbitrarily non-associative. So some demands of the associative laws are still functional, or still can still be still exist. That's the right word. And the Jordan algebra, and this by this he found one important identity for the associator. So this here in brackets is the associator, and the associator of A, B, and A squared always vanish in a Jordan algebra. This is the defining identity for a Jordan algebra. And if you look more into the general case, if you also look at non-commutative Jordan algebras, this was also Jordan's first intention, you have to add another important identity for the associator, the flexibility identity, which says that the associator of A, B, and A always vanishes. And these two identities define the variety of Jordan algebras, general Jordan algebras. We have non-commutative Jordan algebras if the product is non-commutative and non-associative. The first Jordan algebras which were found were commutative Jordan algebras, because they use the commutative Jordan product. For commutative Jordan algebras, we only need the Jordan identity, because flexibility follows from commutativity. But in general, for general Jordan algebra, we need a flexible algebra which satisfies the Jordan identity. This is the definition of Jordan algebras. And here is a list of non-commutative Jordan algebras. They are quite relatively common. For example, the octonions, which are the reason why we are here, and which inspired this whole series, are a non-commutative Jordan algebra. The sedinons are a non-commutative Jordan algebra. So-called Maltsev algebras are non-commutative Jordan algebra, also Lie algebras, and a special variety called quasi-associative algebras, where you just deform the product of an associative algebra by a real scalar. This was also one of the first examples of non-commutative Jordan algebras Jordan found. He never considered them to be quite interesting because one cannot, the only quasi-associative algebra, or which, for example, has a clear physical interpretation, are Hermitian matrix algebras with the Jordan product. This was just for formal reasons, or to show that one can have examples of also of non-commutative Jordan algebras. But this was the part of the introduction of Jordan algebras. Okay. So what was the situation in nuclear physics in the 1930s? This is important to understand why Jordan started his work on Jordan algebras from right from the start, and for later discussions why Jordan was willing to also propose or advocate some radical ideas which today we would consider to be too radical or even non-physical. But let's see how nuclear physics, so the study of the nucleus of the atom, in which situation we were in the 1930s. We had the trouble with the continuous spectrum of beta decay, which some people, most importantly Bohr, used to argue once again that energy and momentum are not conserved in beta decays, and so in nuclear processes, which would of course require a new formalism because quantum mechanics has inbuilt conservation laws. Then we had the famous and now very much celebrated, and at that time also very much valued, Dirac equation, which seemed to predict at that time negative energy states, and even an infinite number of negative energy states. So this was considered to be problematic for the Dirac equation. Then we have, of course, the trouble with the infinities occurring in quantum electrodynamics in the UV and also in the EIR. So we have infinities for very long waves, so for long wavelengths and for arbitrary small wavelengths. This was also hard to deal with at that time. And at that time, people thought that in the nucleus, deep within the nucleus, so what we today would consider to be quarks, there would be electrons. So the electrons we also have in the shell of atoms. In the 1930s, people thought that electrons would also be sitting deep in the nucleus, because in beta decays, and they observed that, well, an electron was coming out of the nucleus, very pictorially speaking, and at that time they thought there were really electrons in the nucleus, and this led, if you look at nitrogen, already to this to trouble with the spin statistic, or the Pauli exclusion principle, because they had measurements of the spin of the nucleus of nitrogen, and they knew, of course, the spin of the electrons, and if you combine both things, they don't add up. You had to propose that in the nucleus the electron is a boson, has a spin of 0, or that the electron spin does not contribute to the spin of the nucleus. And of course, then if you follow this, then you would have to admit or propose that the spin statistics theorem does not apply. And they also noticed that if you use the Heisenberg uncertainty principle, something which I've skipped over, unfortunately, if you use this Heisenberg uncertainty principle for these nuclear electrons, they would have such an uncertainty in their momentum that they would not stick to the nucleus. They should have such a large uncertainty in the momentum that they would leave the nucleus, unless you modify the Heisenberg uncertainty principle. So just to give you an impression how nuclear physics looked at the beginning of the 1930s, some people proposed energy and momentum are not conserved, some people proposed the spin statistics theorem is violated, and some people proposed that the Heisenberg uncertainty principle is violated. So at the beginning of the 1930s, it really looked like nuclear physics is totally different from quantum mechanics and breaks everything. And it took Pauli and other people only a few years to clear stuff up and show that it's possible to sustain quantum mechanics and the quantum mechanical formalism. But at the beginning of in the late 1920s and at the beginning of the 1930s, there were quite a few people who really thought that nuclear physics required a revolution much more dramatic than the shift from classical mechanics to quantum mechanics. And this is also the reason why Jordan was willing to engage in speculations or propose radical new reformulations of physical laws. This is really important to understand, because otherwise it looks like they were just speculating wildly and randomly looking for new mathematical structures. This was not the case, especially not for Jordan. Jordan looked at the Hermitian matrix algebras of quantum mechanics and looked how he could define a product for them. And then he looked at the identities for this product, so the Jordan identity. And this idea was, okay, I know that matrix algebras for observables are already non-associative. If I really wanted to have an algebra, so a system closed under multiplication, maybe I can use the Jordan identity to find a generalization which is still close to quantum mechanics, because I have derived this identity from using the formalism of quantum theory, but is suitable, general enough to deal with the trouble quantum field theory and nuclear physics was dealing at the time. Yeah. Because another motivation for Jordan was that he had a past success with getting around infinities. In one of his first papers together with Oscar Klein on quantizing the electromagnetic field in a non-relativistic setting. This is really important to understand. So it was in a non-relativistic setting. He could show that you can get rid of the infinite self-interaction of the electron or the Coulomb interaction in a non-relativistic setting because of the non-commutativity of the field operators, in this case, of the electromagnetic field. This could not be extended to the relativistic quantum electrodynamics. This was shown 2 years later by Pauli and Heisenberg in a very important paper. But nevertheless, his success with Klein in the non-relativistic setting by using a new algebraic tool, non-commutativity, which was new compared to classical electrodynamics, was inspiring for Jordan, and he even quoted this success from 1928 in 1971 as his main motivation over all these years to look for non-associative or algebraic generalizations of quantum theory, because he hoped by passing over to more general algebraic systems with non-associativity, or later we will see non-distributivity, one might get around the trouble with infinities and other features of quantum field theory. Okay. Any questions regarding this? Nope. I don't see anything in the chat. Then I continue. Also, one very important paper to understand Jordan's later work and Jordan's work on Jordan algebras was a paper by Landau and Piles on extending the uncertainty relations of quantum theory to quantum electrodynamics. And in this paper, they used once, like Fock and Jordan, they used point-like electrons as a probe or as a tool to measure electromagnetic field strength. And they used the special relativity in the sense that they made use of the fact that we have a finite velocity of interactions, the finite velocity of information transfer in special relativity. And they used these point-like electrons, the uncertainty relations of quantum theory and special relativity, to argue that quantum field theory at the time was inconsistent, so it was contradicting itself, which is quite a harsh statement. Yeah, so they concluded that if you use point-like electrons and special relativity, you will get an uncertainty not only for pairs of observables or triplets of observables, but for a single observable. This is a crucial difference to quantum theory. In quantum theory, you cannot measure with arbitrary precision pairs of observables. So you cannot measure with arbitrary precision momentum and position at the same time, but you still have measurements with arbitrary precision, for example, the position operator. In this case, then you get an infinite uncertainty in momentum, which in a sense also is the reason why we have this trouble with infinities and quantum field theory, because for relativistic quantum field theory, you need sharp position measurements to define light cones, and this means that you have a very large, or actually infinite uncertainty in the momentum operators. Or if you use time and energy, then you have to have arbitrarily precise measurements of time, which then gives you an infinite uncertainty in energy. And this is one of the reasons why, we have this infinities in relativistic quantum field theory. And Landau and Perz tried to get around this by proposing that we don't have arbitrary precise measurements for single observables in quantum electrodynamics. And they said that we will have no reproducible and predictable measurements. This means that predictable measurements are measurements where you can say with certainty, probability 1, that you have a certain measurement result. And this is something Landau and Perls said, this is something we will not have, and a unification of special relativity and quantum field theory at that time. And because we don't have any predictable measurements, we don't have any eigenstates, so we cannot develop wave functions. Wave functions do not apply. They compare this to classical trajectories. Classical trajectories don't apply to quantum theory. And in Landau's and Perls' theory, they said wave functions also do not apply because we have much more uncertainty in this case. They also said because we will not be able to, basically we will not be able to develop a decomposition of observables into different into unique probability distributions. We also have no unique probability distributions. And they were on the side with Bohr and said that energy becomes uncertainty and momentum becomes uncertainty, and this is why we have to give up momentum conservation. So this was the situation in the 1930s. And Jordan was not as radical. Jordan proposed his Jordan algebras as a kind of refutation. Later on, this argumentation of Landau and Perls was also refuted by Bohr. Bohr, together with the assistant, showed in 2 papers that we still are able to measure field strengths with arbitrary precision in quantum electrodynamics. Then in 1933 or 94, Pauli proposed his neutrino theory, which then explained beta decay, and people also used the fact that we have vacuum fluctuations in quantum field theory to argue that we do not need electrons in the nucleus. They exist as fluctuations of quantum fields, and if you add enough energy, then a virtual electron becomes a real electron, so we don't need to put electrons into the nucleus. And this relatively swiftly solved most of the problems people had at that time. The only thing which was left was infinities. This was solved later in the 1940s. Okay. Then let's go back to the Jordan algebras. Jordan worked on Jordan algebras for 2 years, and finally he teamed up with Eugene Wigner and John von Neumann to write a very famous paper on the classification of all finite dimensional and formal real Jordan algebras, which again satisfied Jordan the flexibility identity. Which is important, which is also stated in the paper, in the famous 3-man paper on Jordan algebras, which is also stated in earlier papers by Jordan on what's now called Jordan algebras, is that we need power associativity. So the fact that the algebra generated by a single element is associative, this is a necessary requirement to have a spectral resolution in the usual sense, so that you're able to resolve an observable, let's say, an Hermitian matrix into its spectrum, so eigenvalues and orthogonal eigenvectors. Jordan could show in his paper, and also in the 1934 paper, that this will generally fail if you have non-power associative observables. So this is important to get to have a unique decomposition, and for the probability and the interpretation of quantum theory, because the decomposition into eigenvectors is also used to define probability measures and to define the probability law of quantum mechanics. And if this fails, Jordan acknowledged, then we will also have no predictable measurements. And Jordan in 1934 proposed that if Landau and Perls had been right with their proposal, we would have to use something like non-power associative algebras to describe a theory Landau and Perls proposed, the one with non-predictable measurements. So this is also important to understand why going over to non-power associative algebras might be really radical and maybe unphysical step if you try to generalize quantum theory. So once again, here I just show you how Jordan originally introduced the Jordan product. He made use of the addition and the squaring operation. And this operation later on led to a more general product, but in the 1930s, this led to a bilinear, so distributive with respect to addition and homogeneous with respect to scalar multiplication product. This is the Jordan product. Already in 1934, Jordan and interestingly, von Neumann proposed in a follow-up paper. So Jordan wrote this alone, but there's a footnote added by von Neumann where they said, we cannot prove that the product of observables needs to be bilinear. We can only prove that it's bilinear. We can only prove that it's bilinear if it's distributive. Then it's automatically homogeneous, and if it's homogeneous, it's automatically also distributive. So both rules follow from each other, but we cannot independently, so simultaneously justify both rules at the same time. And this later on became a very important step in the development of attempts to go beyond quantum theory. Okay. The trouble with the von Neumann paper and Wigner paper is that they found that there's only one exceptional Jordan algebra, so a Jordan algebra which is not coming from associative matrix algebras. And Jordan's initial hope was that there were a lot of exceptional Jordan algebras, so really fundamentally non-associative Jordan algebras. And they only found one example of 3×3 Hermitian matrices over the octonions, which has only 3 eigenvalues, and this is way too small to generalize quantum theory. So this was really disappointing for Jordan at that time. As I said, he was really what Jordan and von Neumann and Wigner could show that any conjugated symmetric matrix over a division algebra, except from the octonions, for any is a formally real Jordan algebra if you use the Jordan product. And formally real is a condition which makes sure that your formalism is close to working with real numbers. This means that the sum of squares is only 0 if every element squared in the sum is 0 itself. So this is close to the case of real numbers, where the only nilpotent element is 0. And this is something which they require to make sure that you get realistic and real probabilities. So they could show that all conjugated symmetric matrices over the reals and the complex numbers and the quaternions are formally real Jordan algebras under the Jordan product, but they are all coming from associative algebras. Then there was an additional group called spin factors, but they could be embedded into real matrix algebras. And there was only one case where they could show that there's an exceptional Jordan algebra. They initially hoped that also the octonions, also Hermitian matrix algebras over the octonions, would provide examples of Jordan algebras. This is something, if you read closely from the beginning to the end of the paper, so at the beginning of the paper, they proposed or they suspected that also the octonion matrix algebras would be examples of exceptional Jordan algebras, but Wigner showed that for n times n Hermitian matrix algebras for n larger than 3, so starting with 4×4 Hermitian matrix algebras over the octonions, these algebras are no longer power associative and cannot be Jordan algebras, because power associativity follows from the Jordan identity, and Jordan algebras are necessarily power associative. So this basically ended the research on Jordan algebras right from the start, because they couldn't find nice example. Then the Nazis took over, unfortunately. Jordan joined the Nazis. This ended his collaboration with von Neumann and Wigner for his lifetime. And then the war came, so then we have a break in his research on generalizations of quantum theory, which he resumed after World War II. And he looked at the exceptional Jordan algebras again, together with the German mathematician Hase. And what he could find, what he could show is that there's a way to generalize the Born rule for the calculation probabilities also to the case of the exceptional Jordan algebra. And this is probably the most important part of my talk today, but it should be of interest to all people working with the octonions and the exceptional Jordan algebra. Jordan and Hase could show that you can define a semi-definite quadratic form over the octonions for vectors which have 2 octonionic components or 3 octonionic components. You sum over 2 or 3 octonionic vectors. So the x here are octonionic vectors, the x star are conjugated octonionic vectors. These octonionic vectors correspond to idempotents, to primitive idempotents of the exceptional Jordan algebra. And this definite quadratic form over the exceptional Jordan algebra is the analogy to the Born rule in ordinary quantum theory. So with this quadratic form, you can calculate probabilities for example, the probability that one of the 3 eigenvalues of the exceptional Jordan algebras appears in an experiment. So this is a nice mathematical fact, which might be of interest to the people who want to use the exceptional Jordan algebra. What is important is that the components of these vectors need to lie in a quaternionic subtriple. They need to lie in the quaternionic subalgebra of the algebra of octonions. Jordan showed in a paper in 1915, if you use non-associative quantities in this quadratic form, it is no longer suitable as a probability distribution, because then you get negative results and results which do not lie in the interval between 0 and 1. So even though you use it for the exceptional Jordan algebra and octonions, these three vectors these vectors need to have components which are not non-associative. So the components of the vectors need to associate. Otherwise, this generalization of the Born rule does not work. Okay, so this was the part about Jordan algebras and the situation leading to Jordan algebras. Is there anything you want to add or comment? Okay, then I continue. I already mentioned that in a follow-up paper to the famous three-man paper, Jordan also proposed, this, by the way, is this paper. It's unfortunately also only appeared in German. It's called On the Multiplication of Quantum Mechanical Variables 2. The other one was a paper which was written before the three-man paper. And here Jordan just wrote down what I have just said. So there are no exceptional higher dimensional Jordan algebras. So unfortunately, my idea in the sense of Jordan does not work. But at the end of this paper, he proposed in a footnote that maybe generalized observables exist for which the distributivity between addition and multiplication does not exist any longer, and the homogeneity, so scalar commute with operators or associate with operators, does no longer hold. And before I continue with this, I need to introduce a little bit of vocabulary. So there's a nonlinear generalization of the concept of a ring in mathematics, and there's also a non-associative and non-linear generalization of the concept of ring in mathematics. These generalizations are called near rings and quasi rings. So a near ring is a non-empty set with two operations called addition and multiplication, such that under addition, they form a group which is not necessarily commutative. So in a near ring, addition does not need to be commutative. The other thing that is under multiplication, the elements of the near ring form only a semi-group, which in general is not non-commutative as well. So, and which is the most important feature of near rings is that the distributive law between addition and multiplication holds only from one side. So we have the left distributive law and the right distributive law, and in the near ring, only the distributive law holds only from one side. In this case, here is the right-sided distributive law. But there are also near rings where this is inversed, where the left distributive law does not hold, but the right distributive law holds, and there's a lot of discussion which kind of near ring is the right kind of near ring, which I will not go into here. And there's a further generalization of near rings, which is called quasi-ring. In this case, the elements are not required to form a group, but only a quasi-group. So multiplication is not required to be associative. This is important because the algebraic structures Jordan proposed in 1934 do lead to a quasi-ring. So in the end, we will see that there are some mathematical structures which have one-sided, non-homogeneous, and non-associative multiplication. And this was something Jordan followed up on after his work on Jordan algebras, especially in the early 1950s. Okay, but there was something in between. Jordan's work on generalization quantum theory also inspired the mathematician Sassenhaus, who was a leader in group theory and also a leader in the study of so-called near fields, to award doctor thesis to a researcher called Franz Karlsruhe. And Karlsruhe published a paper in 1940 where he quoted Jordan's work on non-associative generalizations of quantum theory as his motivation to look for topological near fields. So a near field is a near ring where the elements form a group under multiplication. So you have an inverse to every for multiplication, and addition is necessarily commutative. You can see it in the book by Pills. But this was quite funny, proven by von Neumann's son. So the son of John von Neumann was also a mathematician, and he proved that in the near field, addition is necessarily commutative. So we are closer to ordinary algebra here. And Karcher looked for topological near fields over the real numbers, and he found that two fields of real and complex numbers are trivial topological near fields over the real number, so they are actually fields, so they're commutative and two-sided distributive. Then he found once again the quaternions, which is a non-commutative but still a two-sided distributive field. So this was a school field to be precise. So this was like Jordan algebra, so it's the trivial cases. But he found a whole family of proper near fields, so which are neither commutative and non-distributive, by deforming the skew field of the multiplication in the skew field of quaternions by a certain process called a Dixon process. The Dixon process basically takes the automorphisms or endomorphisms of a certain field to define a new multiplication. And this was the multiplication Karcher found, and so he could prove that there are proper topological near fields with continuous multiplication and addition, and where you can also introduce a topology over the real numbers by deforming the multiplication in the quaternions. And this was one of the, I think it's the earliest proposal to go beyond linear quantum theory to a nonlinear setting. Here's the multiplication rule. It's quite complicated. This mapping he used to deform the multiplication had to satisfy certain criteria to make sure that we still have an associative multiplication. And he found that the multiplication in the Dixon, so in the Karcher near field, is not altered for unit quaternions. That's why we have to use the norm function here, because for norm of 1, this product reduces to the ordinary quaternion product. So in a Karcher near field, the unit quaternions still have the ordinary multiplication rule of the quaternions. Only for non-unit quaternions, the multiplication is altered. This is important. And here's again the original German paper, and I've marked the section where he quotes his motivation. One was I'm looking for basic axiomatics of mathematics, and the other one is I want to find out what happens, what kind of operators we will find if we give up one of the distributive laws. And this is basically the introduction of nonlinearities into quantum mechanics, because if you give up the distributive law between addition and multiplication for operators, you are working with nonlinear operators. Okay. Interestingly, I've mentioned earlier that the idea to go beyond a linear quantum theory was basically first proposed by von Neumann, and von Neumann then had to escape to the United States because of Jordan's friends, to put it mildly, and he passed over this idea to Irving Siegel, and Siegel then introduced a very general formalism for quantum theory and observables already in 1947. This is a really important paper. Because he was looking for an infinite dimensional generalization of Jordan algebras without having to introduce a distributive postulate. And he could show that we still have a spectral resolution, even if we do not require distributivity and homogeneity. And this is an important step because it shows on a formal level that a kind of nonlinear observable might exist. So quantities which have a spectral resolution where you have a unique probability distribution, but which have not have a non-bilinear product rule, a non-bilinear composition. And this was based basically on a version of the Jordan product where we did not require bilinearity. And as I said, it was non-associative, non-distributive, and non-homogeneous. And on the other side of the Atlantic, there was still, well, between both sides of the Atlantic, to be precise, there was an exchange of papers between, letters between Jordan and von Neumann. So the communication was not totally eclipsed by Jordan's alliance to the Nazi movement. And Jordan published quite a few papers on the possible nonlinear generalizations of quantum theory in the early 1950s. He considered near field and quasi fields, so non-associative near fields, and near rings, and also quasi rings. And something which was new for him was the introduction of mathematical structures with a non-commutative addition. He was careful. He started with the near ring, which was generated by elements where the distributive law is still valid. These are so-called distributively generated near rings. This was a standard strategy by Jordan. If you go beyond quantum theory or the mathematical formalism of quantum theory, try to be as close to the old formalism as possible. So look for the structure generalizing quantum theory, which is the closest to the ordinary formalism. This is something which worked quite well with Jordan algebras, unfortunately too well, because he ended up coming back to the ordinary formalism of quantum theory, but also for his more radical speculations, he made sure that we are still close to the ordinary formalism, as close as possible. That's why he worked with near rings, which are generated by distributive elements. And at that time, Jordan was adopting the ideas from Landau and Peirce and Heisenberg. Heisenberg proposed in a paper in 1938 that for quantum field theory and particle theory, we have to introduce non-certainty for a single observable, and that's why Jordan took this quite seriously, and this was the reason why Jordan was willing to look for very exotic mathematical structures, and also willing to give up the spectral theorem because he was looking for a very fuzzy version of quantum theory. The argument of Heisenberg was that if I try to probe the position of a particle, I have to put a lot of energy into my probe, and if I use a particle at some time, I have some of the energy might be used to excite virtual particles into real particles, and then I have a particle shower, and then I cannot localize the particle, the position of a particle, irrespective of what I do with other quantities and other observables. I have an uncertainty in a single observable, and this really inspired Jordan for the rest of his life. Okay. What Jordan also learned by working on near rings, so on distributive structures, is that in order to have to apply the spectral theorem as we use it usually, you have to make sure that the algebra generated by one element, just by one element, is isomorphic to a classic algebra, so to an algebra of real or complex functions in one variable. We have all the ordinary rules of arithmetic, so commutativity of addition and associativity of addition, associativity and commutativity of multiplication, and of course the distributive law between addition and multiplication. And if this fails, which can happen in non-power associative algebras or in near rings, because the examples of near rings in one variable which are non-trivial, so which are non-distributive, you can no longer apply the spectral theorem. And at that time, Jordan thought without the spectral theorem, I might not be able to have a meaningful theory of measurements. So this was the reason why he quite soon also gave up his work on near rings, because he could not find near rings where one element generates a ring, so a structure where the distributive law is still valid and the polynomials in one variable. He also, there was an exchange between Jordan and von Neumann, and Jordan at that time was willing to give up the linearity rule of expectation values, which he already in the paper in his book in 1930 used as the definition of the sum order of two observables. And at that time, he was willing to give this up and propose a kind of nonlinear relation between expectation values. And this is quite interesting because in Jordan's sense, this work was related to a totally stochastic and random system where you don't have the spectral theorem. But this obviously leads to a link to David Bohm's ideas, because von Neumann used the linearity of expectation values in his famous there are no hidden variables proposal of quantum theory. And this is a link to Bohm's later ideas, even though they had totally different approaches at that time. Then I will just give you a short description of what Jordan did with near rings. So he used functions on a group, on a Abelian group. He used the composition to define a multiplication for this function. He used the ordinary multiplication or composition rule of group elements to define an addition for these functions. So he got a non-distributive nearing with non-commutative addition. He used as the generators endomorphisms of a non-abelian group, so the endomorphisms are still distributive. And then he formed polynomials in one variable. This is as I said, this was a very radical step because he gave up two main axioms of quantum theory, so the linearity of observables and the possibility to have a spectral resolution. So this is a very radical nonlinear generalization of quantum theory proposed very briefly in the 1950s, but also for Jordan this was a little too much, and this was too far away from the ordinary formalism of quantum theory, and nearing theory in the early 1950s was still not developed enough to make meaningful calculations or to propose anything meaningful with this, so he gave this up. Then he proposed to look for a generalization of Hermitian matrix algebras by deforming the multiplication of matrices. So this was one of his ideas to get something which we would call an exceptional Siegel system. He just deformed the multiplication of matrices, of so symmetric matrices, and then he introduced a symmetric product, this product here, which was also introduced by Siegel, to get a formally real algebra with non-bilinear multiplication. So then it's not an algebra, but a quasi-algebra, because this product here, the symmetric product, is commutative and non-associative and non-bilinear. This product here does not have any rules at all. It's non-commutative, non-associative, and non-distributive. It's still power associative. And this was just an attempt for Jordan to show that there are some possibilities to get non-bilinear observables. This product is also called Jordan-Siegel product because Jordan and Siegel introduced it. His motivation to go into this radical ideas was the idea that if you have a minimal length or uncertainty in one variable, you will no longer have reproducible measurements. And his hope for this non-distributivity will lead to a theory different from quantum theory. He could not find nice examples of formal real near fields and near wings. Only this rather artificial example where he formed the multiplication of an ordinary structure. And this was the reason why he gave up. In a follow-up paper in 1952, he wrote, "This is an open question for mathematicians whether some structures exist which have the Jordan-Siegel product and which are not coming from already existing structures, so where I don't have to deform a multiplication." Jordan could not find them. And later on, Loftenslager and Sherman in the US, Ludwig in Germany, a former student of Jordan, by the way, and Alfson and Schulz is here also in the audience, found many more examples of structures which have a non-bilinear multiplication. But unfortunately, there was no correspondence between Jordan and the American school, and also, which is quite interesting, between Jordan and Ludwig. So Jordan found a product, and as we will learn later, Ludwig found structures without a product, and if both had worked together, they would have profited from each other, because Ludwig structures have the multiplication Jordan introduced, and this was a missed opportunity between both persons, and that's why Jordan gave up on nonlinear generalizations of quantum theory. As I said, there were some examples by Sherman and Loftenslager. Once again, these examples where distributivity and homogeneity do not apply. One of the main problems people later learned when they looked more closely into this was there's one paper by Landau, the English one at the University College London, not the Soviet one, who looked at one example of an exceptional Siegel system that, where you don't have a linear multiplication rule. And this example, which was also a rather artificial example, so we have to be careful here, he could show that you're running into conflict with Einstein causality. This is a general problem with nonlinear extensions of quantum theory, because in nonlinear extensions of quantum theory, entanglement becomes, in a sense, malicious. You don't have a kinematical non-locality, but you have a dynamical non-locality. So you have instant action at a distance, and this is, of course, totally in conflict with special relativity. And it's still an open question whether this can this can be circumvented, or whether nonlinear quantum theory is simply incompatible with special relativity. Yep. Another problem with generalizations of quantum theory going beyond Hilbert space is how do you form composite systems? For some structures related to exceptional Fiegel algebras called ordered unit Banach spaces, some notion of tensor product or generalization of a tensor product can be formed. This is quite interesting because normally, if you look at the literature on near rings, they always say we don't have any idea, any way to introduce tensor products related to nonlinear structures. Here, there seems to be some link. This is something which is still an open question, which is something which I put forward here for the audience. I don't know whether this is workable, but it's interesting to see that some structures which are related to nonlinear multiplication rules also have some notion of tensor product. This is quite interesting. Whether these structures allow for something like independent subsystems, so we don't have we don't have any correlations after an interaction. So of course you want to have to have interactions, but after the interactions there should be no action at the distance between both particles which have interacted. And this seems to be also a criterion which singles out the complex Hilbert space formalism of quantum theory. This was one of the reasons why, for example, quaternionic quantum theory never took up, because here you also have the trouble that you have a dynamical non-locality between different components of the wave functions or observables. And Ludwig used the fact that you don't have long-lasting correlations after interactions to and a spectral theorem and the reproducibility of measurements to deduce the Hilbert space formalism of quantum theory. Okay, and I will just go, but maybe I can skip this. This is just a reminder. So we have some non-bilinear observables which have spectral resolution, either also in the spectrum. They have a commutative but non-associative and non-bilinear multiplication. They are, in a formal sense, they're quite generic. They exist for Lebesgue integrable function spaces and for p larger than 2. So they exist on Banach spaces, which are not Hilbert spaces. I think one here in the audience, and he can now jump in and say you're telling nonsense if I'm telling nonsense. I think for the case of P1, Mr. Nestige found this year that one cannot define transition probabilities. For the case P2, we get square integrable functions, so we get a Hilbert space. This is well known. And in this case, the Fiegel Jordan product reduces to the bilinear Jordan product. And for all p larger than 2, so for many Banach spaces which are not Hilbert spaces, we can have exceptional Fiegel systems. So they are, unlike Jordan algebras, they are not quite rare. They are quite common compared to Hilbert spaces, but they have the other problems I said. What's interesting is that people who directly try to generalize quantum theory by working on nonlinear Schrödinger equations found out that the probability or the wave functions in this case don't live on Hilbert space, but on this general LP Banach spaces. So there seems to be a direct link between nonlinear generalizations of quantum theory and exceptional Fiegel system or Fiegel near algebras. In a formal sense, play the same role for observables and nonlinear quantum theory as Jordan algebras do for linear quantum theory. Okay, then I will. Another idea was to generalize vector space. This was done by Johannes Andre here in Germany. He tried to use structures over near fields to generalize the concept of linear vector space. So for this, he used an additively written group and a set of endomorphisms, which then acts as operators to define what he called a near vector space, where the distributive axiom is relaxed. In this case, the structure is more far away from ordinary quantum theory than we had with the general Banach spaces. Here we have the Banach spaces still form vector spaces. Here we have near vector spaces, and in this case, no notion of tensor product can be formed, only direct products or direct sums of near vector spaces. This is closer to the formalism we have in classical mechanics, and maybe this is also the reason why this is a no-go. then he also proposed to use, in 2 papers, to use a Hilbert space or a Hilbert near vector space over a Karlsruhe near field to go beyond quantum theory. This is another way to describe the multiplication in a Karlsruhe near field. And this was his definition of a generalized Hilbert space. He just took the definition we usually use for Hilbert space, but this time it's a near vector space, and we don't take elements from a field, but from a near field. And his hope was that this could be used to generalize quantum theory. Unfortunately, he was working in isolation, so André was working in Saarbrücken, so close to the French border. And for some reason, there was no interaction between André and other mathematicians and Jordan or other physicists. So this somehow disappeared in the literature. There's some fascinating aspect about the Karlsruhe near field. They have the automorphism group of the Karlsruhe near field is the well-known group U1 of complex numbers with norm 1. So also the group is well-known from quantum theory. The commutator group of the Karlsruhe near field is the group SU2C, which is also of unitary matrices of 2 times unitary matrices with determinant 1, which is also used, of course, in the standard model and quantum field theory and to describe spin. The Karlsruhe near fields are really nonlinear, so in this case also scalar multiplication with real scalars does not commute with the multiplication in Karlsruhe near field. Interestingly, this construction Karlsruhe used on the quaternions was then transformed to the octonions by Jordan and by Buchanan and Hale. Then you get a quasi field, which has a quite interesting automorphism group. That's group SU3C, which we use, for example, in quantum chromodynamics. So for this reason, it looks interesting that the Karlsruhe near fields and the Jordan, Buchanan, Hale quasi field might be of interest if you look at nonlinear generalizations of quantum theory, because they have links to structures we already know appear in nature. And another nice feature about the near fields is that they can be represented by 4x4 real skew-symmetric matrices. So you can represent them by on matrices, and maybe these matrices show up in further developments in physics, or they're already here in a hidden sense. And one idea would to look at there's a way to define Pauli matrices using the quaternions, or to formulate the Dirac equation using quaternions. And as the Karlsruhe near field is the nonlinear deformation of the quaternions, one attempt at trying to develop a nonlinear extension of quantum theory would be to use the deformed quaternions and then to try to develop a kind of Dirac equation or generalization of Pauli matrices to have a delinearization of quantum theory. This is an idea one could use because the Karlsruhe near fields have some structures which are related to well-known structures from quantum theory, but they have some other troubles. Yeah. Okay.
Bernd, could I interrupt you for a minute?
Yep.
There's already, I think, lots to discuss with you in question answer. If you have a long way to go, do you think we should do a second talk? We don't want you to hurry through all this.
Okay, yeah, then I will wait. I
How
think
many
this would be
slides
the
do you
last
have?
slide. This would be the last slide for the nonlinear generalizations, then the non-power associative stuff start, and this would be a suitable point to stop here.
How many slides you have in all?
One. So I mean, I still have a lot of slides, but for nonlinear generalizations, I have 1 slide.
So maybe we could do a second talk later on.
Okay.
Do you think that's okay? Because
that's okay. Yes.
Yeah, please go ahead.
So this will be then the last slide on nonlinear generalizations, and then I will also stop. So there was another attempt, this was the latest attempt, I think, to use non-distributive operators in quantum theory by no other than the famous physicist, chemist, and physical chemist and Nobel laureate Ilya Prigogine, who always tried to link thermodynamics with quantum theory and introduce an intrinsic non-reversibility into nature. So a fundamental second law of thermodynamics and not a second law of thermodynamics derived from special initial conditions. So he wanted to have a reversibility right from the start. And he was also unhappy with the measurement problem in quantum theory. and he proposed a stochastic and nonlinear generalization of the Schrödinger equations. And his formalism was based on a generalization of Hilbert space where the elements of the space are not vectors, but operators themselves. So it's on a higher level. So if you have a Hilbert space, you have operators which act on vectors. And in Priogin's construction, you have a kind of space which is formed from operators, and then you have so-called super operators which act on these operators. So this was his proposal. And he found a super operator he called lambda, which was non-distributive with respect to multiplication. So this is shown here. So it's action on a product of operators. So the super operator acts on operators, and his action, its action on operators on the product of operators is not the same as the action of the super operator on one operator and the other operator, and then you form the product. And this is from so the super operators also form nearing, and they also have something in common with the Karlsruhe near fields, because in the Karlsruhe near field you have this relation is no longer valid. So in the Karlsruhe near field, the scalar multiplication is no longer distributive with respect to power raising, and this is for multiplication with real scalars. You have some similarity to the formalism of Priogin. The important thing about Priogin is that he also noticed that you have uncertainty for single observables. So you had a minimum uncertainty for position irrespective of any other observables, and he had a minimum uncertainty for the momentum super operator in this case. And he had a full formalism. So he had an uncertainty relations. He had the stochastic and nonlinear generalization of the Schrödinger equation. And in his formalism, there's no longer a distinction between pure and mixed states. And he hoped to, first of all, get around the measurement problem in quantum theory, and also get around infinities in his calculations. If you so he wanted to basically solve the measurement and the infinity problems of quantum field theory using his formalism, and introduce intrinsic irreversibility into quantum theory and physics in general. And this is obviously linked to Jordan's ideas from the 1950s, but once again, there was no interaction between both. Jordan was already dead at that time, and Priogin didn't, of course, read his old German paper. So once again, it would be interesting to see whether there's any link between Siegel systems, Ludwig's ideas, and Jordan's ideas. So because then you have three different lines which don't work together, and maybe they're working all the time on the same or similar things, and it would be nice if there would be kind of synthesis between both. Okay, and then just to final remark on nonlinear systems. In general, if you have nonlinear dynamical systems in nature or in technology, they can be modeled by near rings. The composition of mappings in dynamical systems is equal to matrix multiplication for finite dimensional and linear systems, but in general, it's not equal. We also have nonlinear dynamical systems. We know that linear dynamical systems do form rings. So maybe if you want to properly better describe nonlinear systems, we have to go to nonlinear systems described by near rings. Nonlinear operators do form a near ring and even a near algebra. And if you think that we need a nonlinear generalization of quantum theory, you might have to go beyond the formalism of rings and fields and go to near rings and near fields. And there's even a recent attempt to solve the measurement problem in quantum theory by using a near ring, by using a mapping. Okay,
yeah.
that it's today.
Sorry, my network broke. So sorry, I couldn't hear your last lines.
The last lines were there was a recent attempt 2 years ago, a paper where they tried to use a near ring to solve the measurement problem. So by adding a nonlinear mapping, which then correctly describes what we call the projection postulate. So because this is a nonlinear process, and there have been ideas and attempts to do this. This was the latest attempt, and with this, part 1 is done. So this was everything about Jordan algebras and nonlinear generalizations of quantum theory. And the next part would then be about quantum logic and non-power associative algebras, and more about Ludwig's ideas.
Okay, thank you.
Okay, so
yeah, thank you very much. Maybe we could take a stop today and then come back later. Thanks so much for this extraordinary lecture. I can assure you this is much more than a hobby. You are a professional. So great. The talk is open for questions. Um, so which year did Jordan die? 50s, is it?
What, sorry?
When did he pass away, Jordan?
In 1980. In 1980.
He lived till 1980.
He lived until 1980, but he became ill in the late 1960s. So I have some letters between him and his students when he was working on power associative algebras. He always wrote, I cannot come to our meeting because I have to go to the hospital.
So which year was he born? I mean,
in 92. So
1902, is it?
1902, yeah.
Oh, so this
he died in 1980.
As young as Heisenberg?
Yes, he was born in the same year as Heisenberg, exactly.
Oh, okay, great. Thank you. David, please go ahead. All yours.
Okay, thank you very much, Tejinder, and thank you, Bernd, for the lecture. Thank you. So I'm a bit puzzled about a comment you made very early on from the 1925 paper about the need to quantize space and time and a hint of non-commutative geometry. That sounds like a very modern idea when we hear that, but in the modern context, we want to combine quantum theory with general relativity, and we know that quantum theory has been very successful over the last 100 years. But over 100 years ago, it is very much in the context of non-relativistic quantum mechanics, I think, and beyond the hydrogen atom, the applications of quantum mechanics were very limited back then. So it seems a very big extrapolation to suggest that space and time should be quantized. Do you know from reading the literature what the motivation might have been, why that should be desirable or even necessary?
Unfortunately, you have already answered your own question as well. Jordan had a tendency to extrapolate extremely wide into the future. He already suspected that we have to, well, he added a footnote, but in his writings, he said already in 1928, I think when the first trouble with quantum field theory showed up, he was quite convinced that you have to quantize space and time. Why he added this in the paper from 1925, I think this was at this time for formal reasons, because it was an aesthetic mispleasing. Why do I use a classical space-time and quantize the field? So why do I have classical variables in my description of quantum theory? In classical mechanics, I also do not use different sets of variables for, let's say, for functions and to describe space-time. To describe fields and to describe space-time. This was at the time where they still thought you have a quite, how do I call it? A strict correspondence principle. So if I use real functions to describe space and time in classical mechanics and real functions to describe fields in classical mechanics, and I replace functions by matrices for fields, I also have to do this for space and time. So at this time, this was more a formal procedure, and he also unfortunately did not quote his motivation. He just said it might be necessary without any further justification. It was only in the footnote.
Right. So the fact that it was already known from general relativity that space and time can have dynamical properties wouldn't have been an influence particularly on that.
At that time, not. Jordan only, let's say Jordan learned relativity by working and reading Pauli's work on general relativity. So he only got really deep interested into relativity in the 1930s when he was working on cosmology. Later on, he shifted completely fields. After World War II, he started a general relativity seminar in Hamburg. So most of his time, or at least most of the students working for him worked on general relativity after World War II, but his interest in general relativity only started in the middle of the 1930s. And of course, after World War, well, at the end of World War II and later on, he developed his own theory of gravity, and then he had this relativity seminar. And he also, in 1971, he said, maybe we have to quantize space and time to quantize gravity. This was only in 1971. So he started early on in 1925, and then there were 46 years of, I ignore everything related to quantum theory and general relativity. And only in 1971, he said, okay, as we have learned, quantization of general relativity doesn't work. Maybe we have to extend to formalism, and although we have to quantize general relativity in the first place. But this is a really strange aspect from our modern perspective, because he was working on generalizing quantum theory, he was working on generalizing gravity, but he never put both things together until late into his life. So there was one paper in 1976 related to renormalization theory, where he said, okay, if all couplings are running and all couplings may be together, then I have to put together my ideas on generalizing quantum theory and relativity. But somehow this escaped him completely. So he was always working on generalizing classical general relativity and generalizing quantum theory. But yeah, and I don't know so why this happened. He never gave specific reasons for this. Maybe he was so completely unhappy with quantum field theory that he thought, I have to repair quantum field theory before I can attempt to merge it with gravity.
All right, sure. Okay, thanks very much. And thanks very much again for the talk. Yeah, thank you.
Thank you. So the next question is from chat. And the question is, firstly, nice talk, thanks, they say. How do the split octonions fit into the discussion?
In general, they're an exciting mathematical structure which should be looked at, which is a very standard answer. If you ask me whether anybody of the Jordan or Ludwig school worked on this, unfortunately not. And at the moment, I don't see, apart from the fact that they also form a non-commutative Jordan algebra, of course, I don't see a direct connection. But if you see a direct connection, if you have to add something, please feel free to do so. Because Jordan also didn't look at the split octonions in his work, so I don't know.
At least in the currently popular work, split octonions have become very important as they seem to help describe chirality in fermions.
Ah, okay,
The split amounts to a change of signature and in essentially parity.
Okay.
So you get left-handed fermions as well as right-handed fermions. That's one use that I am aware of.
Okay. Well, this is something other which is quite interesting because because basically Jordan together with Dirac, but Jordan was one of the first people to pioneer the idea that we have to quantize fields, and he also until the 1930s worked closely on quantum field theory, but after World War II, he didn't follow the research in nuclear physics or on quantum field theory. So he didn't write about entanglement, he didn't write about chirality. For some reason, he did not, I don't know why. So he was more interested in developing new mathematics and to find a new way to describe new formalism for quantum field theory. And I think his attitude was the formalism of quantum field theory is so, how do I call it? So incomplete that it doesn't help if you add more quantum numbers and more properties. We need a better theory which then will also help us explain the features we observe in experiments. But this is a problem because basically after the 1930s, he didn't follow the development in quantum field theory, apart from renormalization. This is something he did follow.
Mm-hmm. Thank you. More questions, please. In the meanwhile, I'm tempted to, quote from Stephen Adler, who's developed the theory of trace dynamics, and where the name trace in the name of the theory, the word trace, comes from the fact that the Lagrangian is the trace of a matrix polynomial, and when you vary the action, you take derivatives of the trace. So it's a trace derivative, and he attributes the first use of trace derivatives to Bernd and Jordan, 1925.
Yeah, this was in a 1925 paper. So,
so
this is also,
I could just read out 2 lines, maybe.
Yeah, please go ahead.
Adler writes, the idea of using a trace variational principle to generate operator equations goes back to the inception of quantum mechanics. See Bernd and Jordan, 1925, who in section 2 of their paper introduce a symbolic differentiation of operator monomials under a trace. They did not develop this idea further, and it remained unnoticed for many years. Then, of course, Stephen Adler makes a new theory using that idea. So it's interesting. I did not know this detail, but
no, the early papers by Bernd and Jordan are really a gold mine. So they started many ideas, which today, as David Jackson said, are very advanced even today, and which were very, very far ahead at that time. It's easy to explain why they did not follow this because of the success of wave mechanics. Wave mechanics just reintroduced the continuum description of nature. The original idea with matrices was really that you have discrete description of nature. And this also went into conflict with, at least if you use the ordinary formalism, with special relativity, because then if you have discrete lengths, then you cannot have arbitrary length contractions, at least naively, you cannot have this. And this for some time stopped. So the trouble with linking quantum theory and special relativity for a long time stopped certain developments.
Yeah, thank you. So it's a historical question. So probably Schrödinger and Jordan probably never met, I suppose. So you think they ever had a meeting? They interacted with each other in physics?
Maybe at a Solvay conference, maybe, but well, I don't know. I would have to look this up. I know that Jordan followed Schrödinger's papers. So when he, first of all, he was a little bit, I'm not convinced of wave functions. But in 1949, when he wrote a paper on the measurement problem in quantum theory, I think it was the first paper where it was called the measurement problem in the title of the paper. So on the problem of measurement in quantum theory, he radically shifted his attitude. He said, not only do we need wave functions, they are not some abstract entity. They're something which are real in nature, which have an objective existence, so an objective feature. And so in a sense, he converted to wave mechanics later on in his life. And he also followed Schrödinger's work on unified field theory later in the 1940s. So you had all papers where Schrödinger wrote on non-metricity and torsion, for example. So this is something where he did still follow Schrödinger. But in the early days, there was really a kind of barrier or between the matrix mechanics people and the wave mechanics people. And I don't know, I would have to look up whether maybe at a Solvay conference or at some other conferences they might have met. But in the early days, there was really this kind of, well, I have to be careful because in his papers from 1926 and 1927 on how to formulate quantum mechanics, he uses already wave mechanics. He uses the Schrödinger equation that he always says it's a nice and wonderful equation. But it's strange because he was one of the pioneers of quantum theory. And he was always unhappy with his own child. So right from the start, with the very first footnote, no, not the first footnote, but with the footnote in the very first paper, he said maybe it's a bad idea to treat space and time classically. Then in 1927, he was, maybe it's a bad idea to work only with Hermitian matrices. Then in 1930, let's work with Jordan algebras. So there was only one book he wrote in 1936, a textbook on quantum theory, where he did not criticize or complain about the formalism of quantum theory we use today.
I think it's probably fair to say that I would think of him as a genius who was probably 1 century ahead of his time.
In many things he was.
Yeah, these things are coming back now, you know, introducing non-commutativity of space-time right into quantum mechanics and the significance of Jordan algebra, especially the exceptional Jordan algebra. I think what may have happened is the success of quantum field theory made people believe that there is no need to generalize quantum theory. And I think the exceptional Jordan algebra is the baby which was thrown away with the bath.
Yes.
Because it is finite dimensional. But I think today we know that it's fine. It's being just 3 by 3 does not really limit progress. Another question.
This is really something new. There was still, after the paper by Jordan and Wigner and von Neumann, hope in the mathematics community that maybe some other infinite dimensional exceptional Jordan algebras existed. Then was put to rest in the 1970s by a Russian researcher who's now working in the US, and I forgot his name, unfortunately. Oh, my bad.
I think he gave a talk on Jordan algebras last year. I am forgetting his name. He gave a talk. Yeah.
Is it Salmanov?
No, I'll have to look up the list.
I have to look up the list, but this was still considered for a long time to be a barrier. And of course, I mean, maybe Jordan came from a tradition of radical change. Political, because he lived when the German Empire collapsed and the Weimar Republic was formed, and also scientifically, when he witnessed the quantum and the relativity revolution. And the quantum revolution, he was quite in the first row, so to speak. And also Heisenberg. And Heisenberg and Jordan always looked for the next revolution, always thought we have to go beyond established science and go beyond more radical ideas. And Jordan and Heisenberg became very ambitious because both tried to develop the final formalism of physics. This is something which you can see, especially in Jordan's case. He wanted to develop a theory where you have uncertainty in one variable and where you cannot resolve lengths any further after a certain length. So which would really be the end of at least high energy physics, because at certain lengths you would not be able to probe smaller lengths. And he was really trying to find a mathematical structure to unify all of physics. And if you look at his scalar tensor series in the 1950s, this was even more radical, because he was one of the first to develop a mathematical series where all constants of nature, not only the coupling constants, also things like Planck's quantum of action or the Boltzmann constant were space-time dependent. So he really tried to...
Yeah, it would be interesting to have Jordan around now.
Yeah, or Ludwig, or some of his followers, and I think the Ludwig followers, which are in the audience, are now a little bit unhappy with me because I did not mention Ludwig in part 1 of my talk. So sorry.
Well, maybe if any of these experts who are present, we are very happy to have them with us. If you would like to tell us something more about Jordan's work and his life, we would be very
Jordan's relation with the can Bernd explain how Jordan and Greta?
Sorry, cannot hear you properly.
We cannot hear you properly. Something is wrong with the mic.
Louder, closer to the mic.
Is this your question with wave function collapse?
Hello, Jitu?
No, he cannot hear us.
Okay, so maybe we come back to him.
Can you hear me?
Yes, this is good.
Okay, fine. Can Bernd explain about the works of Jordan with Greta Hermann, the physicist, the female physicist who challenged Heisenberg?
Heisenberg's uncertainty. Yes. So the first attack on von Neumann's proof that we cannot have hidden variables explaining quantum theory was by Greta Hermann. She was a German physicist, philosopher, and member of the Social Democratic Party. And he was a philosopher in the tradition of Kant's philosophy. And he, in 1932, wrote a very famous book, which is now out of print, and which you can buy for 3,000 euros on antiquarian book sites. So it's a little hard to get.
I guess.
Yeah. And he was the first to point out that there was an assumption in von Neumann's proof of the impossibility of hidden variables, that expectation values are linear, so that or as Jordan would frame it, that observables are linear additive, so that you can add observables. And of course, Hermann didn't keep it by herself. He wrote to Weizsäcker and also to Jordan. Direction of Jordan was, well, I accept that we cannot assume the linearity of expectation values. This was what Jordan took from this exchange, but he didn't accept, or he didn't think that you can reintroduce classicality or get hidden variables with by giving up the linearity of expectation values, because the fact that you can add observables in classical mechanics and in quantum theory would be compromised if you give up the linearity of expectation values. So you would even move further away from the formalism of classical mechanics. The initial hope of hidden variables was that quantum theory is something like statistical mechanics, where you have an average. If you have average over deterministic variables, you get stochasticity and randomness. But you in stochastic in statistical mechanics, you can go back to the behavior of single particles which follow Newton's law and which then are deterministic. So the stochasticity comes in because there are so many particles which interact in a myriad ways, and we cannot keep track of all the interactions, and that's why we have to introduce statistics or stochasticity. But the nice thing about statistical mechanics, as the name say, is that you can reduce it back to classical mechanics, and you don't lose any algebraic structure. So you can still, so the hidden variables, so to speak, so the momentum and position of single particles in a gas, they still obey the linearity of expectation value, which in the case of variables which are stochastic is just the value the observable takes. And this doesn't work in quantum theory. This was something which Bell proposed. So suppose we do have a deterministic complementation of quantum theory. In this case, the eigenvalues of our observables would be what gives rise to the stochasticity, the expectation values on the coarse-grained level, and eigenvalues of quantum mechanical observables do not add linearly. So if you take the eigenvalue of the position operator and the eigenvalue, a certain eigenvalue of a momentum operator, and if you add them together, they don't obey a linear relation. So it's not like a 1 + 2 is 5, but you get something different additionally. So you have a nonlinear, addition was probably not the right way, composition of eigenvalues for those operators in quantum theory which do not commute. And the question is now, why do classical mechanics, stochastic statistical mechanics, and quantum theory have the linearity of observables? And this would be the right moment of time for Gerd Nystigge to jump in, because he has worked on this for some time. So why do we have linear structures of observables in physics in all of the theories we have so far? This is something everybody who wants to introduce non-commutative addition, for example, or who wants to circumvent von Neumann's no hidden variable theory has to explain. So because if you try to circumvent his theorem, you have to introduce variables, coarse-grained variables, which have a nonlinear addition rule. And the question is, well, why does nature observe this rule? So Bohm, of course, thought about this deeply. He wrote it in a letter to Jeffrey Bobb, and they also published 2 papers about this. And Bohm said that if you do not have a linear relationship between expectation values, you have a kind of Machian universe. So the macro level determines the micro level. So micro variables are determined by the macro level. This is a quite, I think today one would call it top-down causation or top-down determination. It would be that not only the whole would be more than its parts, the whole would define its very parts. So you would not be able to define, to distinguish between the components of some global structure, or let's say you have an ensemble of particles. The very observables you need to describe the components of this ensemble would be defined by being in this ensemble, by being in this global structure. And this is something which Bohm later on acknowledged, and which he used in his books, in his paper. He wrote about this implicate order, and which is also something Basel still follows. So Bohm and Basel and Bobb learned the lessons. Of course, this means that you will have something similar also if you go to observe to a structure with non-commutative addition, because the commutativity and associativity of addition is a requirement for having linear expectation values. This was something which Jordan already proved in 1932. And this was also one of the reasons why he did not look into the structures, because he said, we have a clear meaning for addition of observables, the classical mechanics and the quantum theory. And if I change this, then I have to change the whole structure and also the possibilities to do measurements. And in this case, the measurement setting would influence its own results. So it's really interwoven and intermingled everything, and it would be really hard to distinguish this. And I think this is one of the reasons why this was not proposed any longer. But Jordan did not look into this. So this was something which Bohm found out. So Jordan wrote to von Neumann in a letter which I showed, would it be possible to have a nonlinear addition law for expectation values or observables? What do you think? And unfortunately, von Neumann did not write back, or at least they didn't came to any kind of conclusion about this. So I don't know. So I had to read Bohm. to understand what this all means, because in the second part of the lecture, in the lecture 2, you will also see that there are some links between Bohm's ideas and Jordan's ideas on non-power associative algebras. But at the moment, yeah, I cannot answer this. Apart from you have to introduce top-down causation.
Can I ask another question? You mentioned a book which is written together by Max Born and Pascual Jordan. Can you name that book? I was unable to find that. Any link or something?
Yeah, the link. It's called. Well, it's called. What? It's in German.
Questions, please? Other questions?
Yes, I have a question which is apart from Jordan's work, but it's related to EPR paradox.
Okay, sorry.
I have heard, I have read the EPR paradox, the original Einstein's one, and I was unable to find things like a hidden variable, realism in that paper. There is also some people say Einstein didn't mention about hidden variables, realism and on, but he was totally emphasized on the locality of the information that gets traveled.
Well, so what the Einstein?
Is that correct? Hidden variables has nothing to do with Einstein, but it has to do with David Bohm, who actually reformulated the paper in terms of hidden variable theory and experimentally verified it.
Well, as far as I know, well, Bohm was able to reformulate quantum theory as a hidden variable theory by making sure that the deviations from quantum theory are hidden. He introduced the equilibrium condition, which makes sure that you have not access to the hidden variables. What Einstein and Podolsky and Rosen showed is that, well, the predictions of quantum mechanics would lead to non-local interactions if you believe in pre-existing properties of particles or things like this. So if you want to complement quantum theory in a realistic setting, you have to introduce some non-localities. This is basically something, yeah, what was the conclusion of this? Because what Einstein was interested in was the realistic setting of quantum of reality. So he wanted, well, particles or objects in the universe to have pre-specified properties which are not dependent on interactions with the environment or on somebody at that time measuring it. And the Copenhagen interpretation said, well, basically a particle does not have a definite value of momentum or position until you measure it. Before you measure it, it simply doesn't have a specific position or a specific momentum. And this was something Einstein objected to. And the EPR paper showed that, well, if you have something like pre-specified properties of particles and try to explain quantum theory, the formalism or the results of quantum theory, you have to introduce some non-locality. And this was also a little bit unwelcome by Einstein, because Einstein was also, what Einstein wanted to have was a local and realistic theory. And the only thing at the moment where you can get this is by read Sabine Hossenfelder's papers to have something like superdeterminism. So where everything is predetermined right from the start at the Big Bang. Otherwise, you can, and where you, in a sense, where you don't have where the results depend on your measurements.
Well, I have a question that people also assert Einstein had a bias that quantum mechanics is deterministic, but Einstein, in Einstein's academic career, Einstein was a statistical physicist. He pioneered the, I mean, he done very influential works in statistical physics. So yes. Einstein also knows the importance of probability in physics. So why Einstein should again go against probability in quantum mechanics? I don't understand. Please.
Well, he was against irreducible stochasticity. So in classical, in thermodynamics, we also have probability, but there's a deterministic background. So basically, if we ignore quantum theory for the moment. If you look at, for example, you have a simple thing like a gas. There are many, many particles. You look at the Avogadro numbers, and you simply don't have enough information to keep track of all of the particles. That's why you introduce stochasticity. But if you look at every single particle, it still follows Newton's deterministic laws. And this is something Einstein wanted to have. Einstein wanted quantum theory to be complemented or supplemented by an underlying theory, just like statistical mechanics is based on Newton's mechanics, on local and deterministic interactions. This was
I could just add that Adler's trace dynamics is a step precisely in that direction. Trace dynamics is a deterministic, though non-unitary dynamics from which stochastic aspects as well as unitary aspects of quantum theory are both emergent.
Okay, then you would also have to explain to me how you get around von Neumann's proof. How do you get around?
The thing is that the underlying dynamics is at a level of resolution, say in time, a level of resolution which is not the same as that of quantum theory.
Okay.
Hidden variables are at the same level of resolution as the rest of quantum theory, whereas trace dynamics is more microscopic than quantum theory. So you get quantum theory by coarse graining trace dynamics.
Okay, this is maybe I should be more careful about the statement concerning von Neumann. So what von Neumann said, if you
have underlying theory, which is from which you coarse grain to get quantum theory, then the variables which you are coarse graining over are not hidden variables. Just as atomic motions in Brownian motion.
Okay. So you get around because your variables are not hidden.
Yes, they're not hidden.
Okay, then you don't also have that you don't have the trouble with von Neumann's proof that hidden variables require giving up linearity of expectation values. But if they are not really hidden, and of course this is also better from an epistemological point of view, because then you would have the possibility to have measurements which distinguish between your variables, the coarse-grained variables in quantum theory, because if hidden variables stay hidden, well, they're just hidden.
Yes. Yeah, but also, but I want to come back to Jordan algebras. I had a couple of questions. So the first is that, the exceptional Jordan algebra, which we usually call J38, it is known that automorphisms of this algebra preserve not only the inner product, which is a quadratic form, but also a triple product, which is not typical of the classical Lie algebras. So as you know, the automorphism group of J38 is F4.
F4, yes.
Second exceptional Lie algebra. And those automorphisms preserve a triple product. And it's a curious question. What is the physical interpretation of the inner product? We understand in terms of lengths of vectors, but here something new is coming up. So I don't know if Jordan was aware of this.
No, he was not. This came later. So I know about. Are you talking about the Freudenthal product?
Yeah. Freudenthal product is slightly different.
And there's also the so-called Jordan triple product.
Yes, that's the one.
Okay.
That's the one.
Jordan was not aware of it, but mathematicians in Germany in the 1960s and 1970s worked with Jordan triple systems, and they showed that there's a link between symmetric Riemannian spaces in Jordan triple systems, and in some cases the curvature of these spaces is linked to the triple product.
Okay, so they also said to go beyond Riemannian geometry and symplectic geometry to something known as metaplectic geometries, which I don't know much about. So maybe we'll talk about it some other time.
Some other time, yeah.
And second, the Freudenthal teeth's magic square, as you know, the fourth row involves the exceptional Jordan algebra. So did the Freudenthal and Jordan historically, do you know if there was any interaction?
No, and in this case it was easy. Well, Jordan stumbled his own career by becoming a Nazi and being part of the stormtroopers. And most scientists in Europe and the US and also in Germany after World War II tried to avoid him. And especially people from states like the Netherlands, which were occupied and terrorized by the Nazis.
So this is after the war also, it continued.
Yes, there's even there was once in the 70s, there was once a student who was traveling to Hamburg, so where Jordan was based, and he wanted to talk to Jordan. So he asked at a
this is the 70s, is it?
In the 70s, it wasn't in it was still in the 70s. So there was a student traveling to Hamburg because he wanted to talk to German. Then he went to Jordan's office and asked, "Is Jordan here?" And then there was a student saying, "No, he's not here. He's ill. This was a lie." So Jordan's office kept people away from Jordan because they didn't like Jordan. Because Hamburg was a very left-leaning and social democratic city before and after the Nazis. So he was kept in isolation in Hamburg, and he was he was always running out of money. So there were some conferences here where he was invited to, and he could not come because he could not afford to buy the ticket or to cover the hotel costs. So he was quite poor. Then he became ill in the 1960s, and he was basically issued by many of his colleagues after World War II, and also by many of his students. Not all of them, of course, but once somebody was trying to visit Jordan, and then he was sent back by Jordan's office because the people working in Jordan.
Is there a scientific biography of Jordan that someone has written, or there isn't one?
There is one to be published, hopefully next year, by Wayne Dunn from the US. He wrote his PhD thesis on Jordan, and he's writing at the moment a biography of Jordan. He hopes to publish it in 2025, 100 years after the famous 19. So we are about to get one, and I'm at the moment working on a book describing Jordan's ideas, and I hope also to get it published in 1925. 2025, 100 years later.
Just add that
with some hope, we will have 2 books about Jordan next year.
Okay. Some of us believe that the exceptional Jordan algebra is extremely important for describing 3 generations of fermions. And the reason why there are 3 fermion generations has everything to do with the fact that the 3x3 octonionic matrices are the only one allowed in the Jordan algebra when you deal with octonions.
Yes, because afterwards you don't have any Jordan algebra and you have a non-power associative algebra.
And as you of course know, the fact that there are no octonionic projective planes beyond n equals 2, beyond OP2, is directly related to the fact that beyond the 3x3 matrices, you do not have Jordan
algebra. Yes.
Yeah.
This was a kind of compensation for Jordan. He always wrote in a paper in 1952. It's unfortunate we don't have any exceptional Jordan algebras beyond 3x3, but at least there's a nice theorem showing why this is the case, because there are non-Argesian projective geometries larger than dimension 2.
I see your remark here. And my second point was that the eigenvalue equation for the exceptional Jordan algebra, the characteristic equation,
which still works because we have a power associative algebra, yes?
Yeah, it was developed by Corinne Minogue and Tavian Ray. Maybe, I don't know if anyone looked at it before that. That's probably, at least in my work, an extremely important equation. The eigenvalues of this equation, suppose you take the matrix entries as octonions, which are representing spinor states of fermions. So you have 3x3 matrices, 3 fermion generations, say electron, muon, and the tau lepton. You put their octonionic spinor states in. The diagonal entries are the electric charge, which is in this case 1 in fundamental units, and you find the eigenvalues. They are very interesting. They are numbers, they're very simple numbers. 1 minus square root 3/8, 1, and 1 plus square root 3/8. And I believe these have very far-reaching significance. So there are 3 real eigenvalues when you solve the characteristic equation of the exceptional Jordan algebra with octonionic entries representing spinor states of 3 generations of fermions. So the eigenvalues are 1 minus square root 3 by 8, 1 and 1 plus square root 3 by 8. And this seems to have a lot to do with the determination of values of dimensionless fundamental constants in
this
the
would be really fascinating indeed. So, and of course, this would show that we that you don't need to go beyond the exceptional Jordan algebra if it contains the fundamental coupling.
Yeah, to my understanding, the exceptional group E8, which really is builds from the exceptional Jordan algebra and F4. I mean, E8 is like F4 times F4, and F4 is the automorphism group of the exceptional Jordan algebra. So I think that everything we need to know about standard model and gravitation is contained in the exceptional Jordan algebra, and we don't need to go beyond the exceptional Lie algebra. That's my understanding.
Okay.
That's why your talk on Jordan's work are extremely important. And
what do you think about Jordan's generalization of the Born rule for the exceptional Jordan?
This is new. Thanks so much for presenting it. I have not used it in my work. I've seen it in your earlier remarks, and I've seen it in the emails that you have sent it in our correspondence. I definitely will think about it. It's very, very important. So you are saying that if, say, we go down from octonions to complex numbers, this probability rule, this quantity Q, will just become mod psi square in the ordinary Born rule sense?
That's a really good question. I would have to look up and send you also the proofs. There's one paper where Jordan deduces this probability rule, whether it's important that you have real coefficients and not complex coefficients. So at the moment, I cannot answer this question. It could be that it's really confined to the real setting, but I don't know. We'll have to look at...
My handicap is that his work is in German, and I never learned German, and so
that's why I'm writing this book, to translate his work into English so that other people have a chance to...
Okay, so this will this will be coming up next year, is it?
Hopefully, yes.
Okay, great. And more questions, please. I think we are getting...
it's to Dr. Burns. I have heard a story that Pascual Jordan and Max Born actually figured out the uncertainty principle first, then later Heisenberg was the one to publish it. So
this is actually true. Yes. So yeah, this is true. They published they figured it out.
And there is also one thing I have read from Roger Penrose's Road to Reality, that the Heisenberg actually forgot how to do the Poisson brackets. That's why he came up with the he forgot something. That's why he came up with the matrix things. And there was also a remark made from Max Born that I don't understood. I didn't know what Heisenberg was doing under my supervision when he was doing his PhD.
This is true. This is, as I said earlier, there's this, well, as Jordan later recalled, so there was at that time, so I don't want to downplay the intelligence and the qualities of Max Born, because he was still a very important figure, also inspiring Jordan's work later.
Actually, I think
but there's really this yeah, how do you call it? This story Jordan told that how got Jordan into matrix mechanics. Well, Born learned that Heisenberg was working with matrices. So initially, but that's normal. So if you're exposed to a new mathematical structure, a new finding in science, 99% of all people don't immediately see what you're doing. And when he first saw what Heisenberg was doing, he thought about it, and then he noticed, okay, it had something to do with matrices. And he knew at that time that he was not an expert in matrix mathematics. So but he talked to his students during a train travel, I think to Göttingen, about, so I've worked with Heisenberg. Heisenberg has found out something about matrices, that matrices might be useful in describing processes in atomic physics, and I am no expert in matrix mechanics. And this was basically the starting point for Jordan's career, because Jordan was listening, and then he said, but I'm an expert in matrix mathematics or linear algebra. I've been working with Richard Courant on this, and maybe I can help you. And this worked, so he really helped, yeah.
Dr. Bernd, does that mean Heisenberg didn't knew linear algebra?
What?
At that time?
Of course, they knew linear algebra, but it was not. It was also in use, but it was not in so matrix theory was not much in use at that time, apart from crystallography.
Oh, okay.
You can look at the handbook.
Nowadays.
So of course, they knew about linear algebra, but it was not much. So at least the aspect with matrices was not very much in use. Of course, you had already tensor calculus and tensors for general relativity. But applying matrices to describe observable systems, this was something quite new. So to use it as an as a mathematical structure to represent structures of observable structures of reality, like position and momentum, this was not much in use at that time.
Thank you. Thank you. So maybe we should proceed.
And never underestimate the mathematical abilities of people 100 years ago. There was once a handbook of physics, which was published, first in Germany in the 1920s to 1930s. And there's one mathematical methods for physicists. And this is really tough going. I mean, this book also from in the middle of the 1920s, this is really still far advanced for today's students. They talk about torsion and non-metricity. So they were really keen also at mathematics at that time.
Mm-hmm. Dr. Burns, is the elementary quantum mechanics by Max Born and Pascual Jordan coming up in English?
We are now living in the age of artificial intelligence, and fortunately enough, some of the very old books were digitalized by Springer, and you can buy German reprints of this old book from 1930 from Springer. And it's also as a PDF file available. So I hope that in the future, somebody will put this into an artificial intelligence and produce an English translation of all of the old German books. So this would be much easier, because even if I'm writing a book at the moment, I cannot translate all of the works of Jordan, put it into one giant book. But I hope that maybe we can talk to Springer, or somebody could talk to Springer, that some of the books which are now available in German as PDFs will be translated into English, so that the rest of the community has a chance to understand what the old people did. Because in the 1920s, until Jordan's friends came up, German.
Say something.
He was asked, there's still a question whether wave function collapse is part of the matrix formalism. In the very early formalism, where they use discrete matrices, there's no need for wave function collapse, because you have really literal quantum jumps. So the system on its own jumps into a certain state. This did not work. So we still use a continuity description of nature. And as matrix mechanics with infinite dimensional matrices is isomorphic to wave mechanics, it also doesn't have any wave function collapse or jump of states. It still has the unitary evolution. It's only that in this case you use a matrix with no wave function collapse.
Jitu, could I request you to kindly get in touch
with fine.
Personally, please, because it's past 2 hours.
Yes. Anybody else or anything else?
Michael, are you there?
Yes, I most certainly am. Tejinder, I'm simply flabbergasted by the amount of ground that Bernd has covered today, and can only thank him for a really quite prodigious performance in terms of clarity, precision, and as I say, going very, very deep indeed into a subject which I think to be presented with this amount of carefully controlled exposition really does take a remarkable talent. So thank you very much indeed. I can't say how much I've learned from this. I see connections all over the place of various topics, but about those perhaps we can correspond directly or
Yeah, so
via
I can
email.
also
I
put
don't
my
want to
email
break that
address,
now, but
of course, in the chat.
it's been absolutely fascinating. Thanks.
Yeah, I agree totally with Michael. The extraordinary, beautiful lecture.
Yeah, yes.
A lot to learn.
Unfortunately, yeah, I put too much into it. Next time when I give lectures, I will make sure that I split them up into
Well, no, I mean, you could easily have turned this into 3 lectures, but don't criticize yourself for that. You really did do a
no, that's okay.
masterpiece of
This
compression
is
and
always a
exposition.
problem that I want too much at the same
No,
time.
I wouldn't agree.
Okay.
I think you made the absolutely optimal use of the time. I really do. I'm not saying that to be courteous. I just can't
Okay,
thank enough for having gone so
here,
thoroughly into it.
Francesco
We certainly would
Topan.
like to hear you talk again and further, and I think I speak for everybody. We're looking forward to the book enormously.
And I'm not writing this alone. So Manfred Liebmann, who's also here in the audience, will contribute to it, and Mahfoud Kakali from Canada, an expert in commutative geometry, he will also contribute to this book.
Yes. He's somebody I've been very interested in. You mentioned, by the way, you mentioned the role of Greta Hellman in this story. May I just recommend Guido Bacigalupi's very nice book about her work and her.
Oh yeah, can you? Well, you have my email address. Can you send me the link?
Yes, I certainly will. Yes. Well, thank you again.
Sorry?
I say thank you again. I was
thank you.
If anybody
Thank you
else
for giving me the opportunity. And yeah, maybe we can discuss when I give part 2 on the 1960s. So everything apart from the octonions, if you go into the realm of non-power associative algebras, and I have to express my apologies to Francesco Topan because he's working on non-power associative algebras and he was here for for free. So sorry that I did not cover non-power associative algebras.
I hope we will have the next in the next lecture, right?
Yes, it will be in the next lecture.
I was impressed. I was impressed. I was really flabbergasted because of all these what you mentioned, and I found a lot of connection with something very recent.
Yes,
you mentioned about the relation between non-hermiticity
with recent ideas.
Absolutely amazing.
Well,
thanks for having invited me.
You're welcome, always. And the second
thanks to everybody for coming.
To Gerd Nittiger for not covering Ludwig's work.
We have free slot in October, so perhaps we could fix your second talk there. Okay. Michael, if you are okay with that, we could do it next year, whichever way.
It would be good if we could have it sooner, whilst your talk today is reasonably fresh in our minds. So I'm all in favour of having another bite of the cherry in October if Bernd is up.
I'll get back to you, Bernd.
Okay, get back. So I would be available in October.
Right.
Unless the flu catches up again. But apart from this.
So any more comments from anyone else who's still here? Otherwise, we'll say bye to each other. See you next week. We have a talk next week, Friday, June 21st.